All right, everyone, welcome to the New York Combinatorics seminar. We're happy to have Aditya Khanna, who's going to tell us about matrix inverses using pictures. Okay.
Thank you so much for the introduction, and thank you to the organizers for inviting me to this seminar. All of what I'll be talking about is joint work with my advisor, Nick. I give a short version of this talk here at JMM, and so this is the uncut and uncensored version. So let's begin. We'll start with matrices, right? What is a matrix? You take a matrix M, and that is basically just a map between two vector spaces, V and W in this case. And what you want to imagine this is as a map between bases, right? I take a basis from here and I'm trying to transform it into a basis of vectors on the other side. Okay. Oh, one second, I'm getting a call. Hello? Yeah. No, I can definitely do that. Yeah, sure. No, that makes sense. Totally. Okay. Yeah, thanks for letting me know. So I've been informed that as I'm in a combinatorics seminar, I have to talk about combinatorics. So let's start again. We start with combinatorial matrices. So matrix is called combinatorial if any of its entry can be expressed as the signed sum of some objects. I'll explain what that exactly means later, but this is the idea. This is a -1 as an entry, and the way I will calculate this -1 is as a sum over 3 objects. Say 2 objects are weight half, and the other object is -2. I add them up, that gives me -1. That's what a combinatorial matrix is. All of its entries can be computed in such a way. A very famous example, they are called Pascal matrices. You know what these are. I have this 5 by 5 matrix, and the entries of these are,
I know your coefficients.
I know coefficients, and you know how to compute them. I get a 6, then I do a column choose 2, which is column choose row. So this 4 choose 2. That's the algebraic way to compute it. I get this, but these are counting some objects. What are they counting? They're counting number of ways to fill 4 boxes with 2 identical balls. All of these have a weight of 1, like 1%. And what is this doing on a fundamental level? It is a map between 2 bases, and the 2 bases are 1 plus x to the n and x to the n. These are 2 bases of your polynomials. You can say maximum n degree polynomials, capital N degree. And this is the famous binomial coefficient. Right, binomial theorem, we have all of this. This is something that you have seen a lot. What I want to talk about are not Pascal matrices. That is not my field of study. What I'll be talking about are these things called Kostka matrices. We will definitely describe all of it. What are they indexed by? What are the entries? We'll talk about it. That's the whole talk. That's not the whole talk, but we'll talk about this. But before that, I want to just tell you where we are going with this. Right? I have Kostka matrix. I'll describe some pictures associated to it. Then I will tell you why we care about them, like what is the matrix mapping between. Then we'll see some recursion. And that recursion will actually allow us to construct an inverse in some sense. And then, so the 4 things on the top, they're known already. So that's the background that has already been established. This is our work. And how can we use those pictures to show that these 2 things are inverses of each other? And then I'll give a global bijective proof, which if you have any semblance of what this field is, this is pretty cool. It's like a canonical bijective proof of the Kostka matrix. Okay, let's get started. What I want you to keep at the back of your head that this is a general framework that I'm describing, but I'm doing it in terms of an example. In our paper, we have 4 different applications, but I'll be only focusing on one of them, which we think is the stellar application. But at the back of your head, this is very general. So we can also talk about how you can probably apply this to your field. Let's start with what the indices were for the matrix. Our combinatorial objects that we'll be working with are called compositions and partitions. A composition is simply a list of numbers that add up to a given number, n. So in this case, 3, 1, 2, 3, 3 plus 1 plus 2 plus 3, 9. And the way I will deal with compositions will be to I will first write them as a list. Also, I will denote them using diagrams. And the diagram will be just 3 boxes on top, 1 box in the second row, second, 2 boxes in the third row, and 3 boxes in the fourth row, so 3, 1, 2, 3. If you arrange them in weakly decreasing order, they form what is called a partition. So composition partitions, whenever I say compositional partition, you should have both of these ideas floating on your heads in your heads simultaneously. And we're combinatorialists, we see boxes, we want to fill them with stuff. So in this case, lambda is a partition, beta is a composition. That will be very important. And this will be mostly what I'll be using. Lambda, mu, gamma will be partitions. Beta and delta, alpha, they will be compositions. But I will make sure to tell them. So how are we filling these? The fillings have a certain rule to them that when you go from left to right in a row, you can either increase or stay constant. So they are weakly increasing. But when you go down, they must always increase. So these are the two conditions that you have. The semi-standard part, this is called semi-standard. The semi part is because you have equality sometimes. And so this will be called a semi-standard Young tableau. It has 2 components to it. One of them is a shape. What am I filling? What are the boxes forming? As you can see, there are 6 boxes on top, 5, 5, 4, 3, 1. And that is my partition. What am I filling? And then how am I filling it will be captured using a composition. So I see how many ones are there. There are 3 ones, so I put a 3. There are 5 2s, so I put a 5. Then 3 3s, 4 4s, 2 5s, and 3 6s. That gives me a composition. So the ith entry of the composition is telling me how many of those numbers I have. And this is called a content. So then I'll call this a semi-standard Young tableau of shape lambda, what am I filling, and content beta, how am I filling it? Questions? Is everybody good with the definitions?
And the partition and the content don't necessarily uniquely determine the semi-standard given template. Is that right?
No, there are multiple ways. It's a good thing they don't uniquely determine because of what we'll be talking about next.
Can 0 even go some bad? We know such fillings?
I will get to that.
Okay.
But yes, very good question. Anything else? All good? Going once, going twice. Okay, moving on. So they're not unique, and that's great because the Kostka matrix is counting the semi-standard Young tableau of a given shape and of a given content. So for example, if I look at this, in this case, I have partitions in my rows, so that will determine what my shape is. So my shape is 3 2, and I'm filling them with 2 1 2 content. So 2 1s, 1 2, and 2 3s. And these are the 2 that you get. And that's where the 2 comes from. Another example is this 3, and this 3 is the shape 3 2 again. And 2 1s, 1 2, 1 3, and 1 4. And that is your number of semi-standard Young tableau. That's what your Kostka matrix's job is to. And in general, this is called a Kostka number in row lambda and column beta, partition content. And we will denote this by either k lambda beta with parentheses or k lambda beta in the subscript, depending on how much space I have on the slide. And this is called a Kostka number corresponding to lambda beta. Right, I did say matrices map between some stuff, right? So what are these Kostka matrices mapping between? Now we're going to shift from combinatorics to algebra. If you have a preference for any of them, you're welcome to take a nap right now. So what are we going to be talking about are these objects called symmetric functions. That's my main object of interest. And like Pascal matrices for mapping between these polynomial bases, we'll see what bases they're mapping between. Instead of polynomials, we have symmetric functions. So what is a symmetric function? A symmetric polynomial is that if I start with something like this, and then I swap all the variables, and I compare to the original function, I see that there is a y squared xc here, y squared xc there, yx squared c here, x squared yc there, yxc squared here, and xyc squared there. They all match up, they're equal. So it did not change under swapping. This is what we wanted. A symmetric function is the power series version of this. Infinitely many variables, right? throw all of them together, and any sort of swap between variables will not change it. So symmetric groups are generated by permutations. Any permutation that you can do on the indices will preserve the variables. So this is what a symmetric function is. Wherever there is symmetry, there are symmetric functions. One of the simplest example in some sense is I take all the monomials of degree n. Right? You can't stop me from doing that. How can you make a monomial of degree 3? By putting cubes. How else can you do it? By quadratic and linears, or taking 3 linears together. And now if you swap anything, the degree will remain the same. So monomial will just become another monomial, symmetric. Right? Very cheap way of constructing these things. This is called Hn. So H sub 3 is this. You can define it for a composition. So you can slightly extend this idea. So H indexed by a composition is just the product of H's indexed by the parts of the composition. So H4314 is H4 times H3 times H1 times H4. Product of symmetric functions are symmetric. Addition of symmetric functions symmetric, so everything works out. So this is one guy, right? Store it away at the back of your head. Let's talk about another slightly more complicated example of, okay. Also, just to be clear, if you take all H betas for compositions beta, they form a spanning set for all symmetric functions. Not a basis, spanning set. So keep that at the back of your head. Let's talk about Schur functions. Probably the most famous example of symmetric functions out there, very important, generalize everything. The way to define it is using the semi-standard Young tableau that we started with. I give you a semi-standard Young tableau, and to each of that, you can associate a content monomial. How would you do that? Well, I gave you the content before. You just take the content, and every ith part of the composition will be to the power of xi. So it will be x1 cubed, x2 to the power 5, x3 cubed, x4 4, 5 squared, and x6 cubed. So if there are some number of i's in your tableau, your xi will be raised to that number. So for each I, you can associate an xi and then multiply them together. And so this gives you a monomial for each semi-standard Young tableau. So if I give you all semi-standard Young tableau together, right, and then you sum over all content monomials for a fixed shape, that is called a Schur function indexed by that partition. We'll see an example in a second. But this is the main idea how to construct these. Why are they symmetric? I'm not going to tell you that. There's a proof behind this. But they are symmetric. Very nice. This is where the question was raised that could there be zeros within the composition? Yes, there is a slight caveat here that some fillings might not exist. So I might fill 1, then 2, skip 3s, and then fill 4s. So now I'm allowing zeros in my composition, but only for this particular time. For the rest of the compositions don't have zeros in them. So thank you, little friend, for telling me that. So let's look at an example for the Schur function. I start with my shape 3, 2, and I fill it with 3 1s and 2 2s. So that's x1 cubed, x2 squared. Then I fill it with 3 1s and 2 3s, so 0 for a 2 in the second place. And that will give me x1 cubed, x3 squared. Then I have 2 1s, 1 2, 2 3s, and that's exactly what you get. I could fill it with 1, 2 2s, 1 3, 1 4, or I could fill it with different numbers. And I could do that in all possible ways, right? For every filling, every natural number, I do that. And if I add all of these up, I get what is called the Schur function of 3 count. So what are Kostka numbers doing? The Kostka numbers are basically, the Kostka numbers, what they're doing is going from this spanning set to spanning set by the edge functions to this basis described by the Schur functions. So symmetric functions, their bases are indexed by partitions. And so this is what we're doing. And that's why we saw the matrix was rectangular. There is a better way to understand this using something called non-commutative symmetric functions, where these could be actual bases, but In our case, we care about rectangular matrices. Questions? So now let's go back to, we went from combinatorics to algebra, back to matrices. So let's look at this guy. I have 2 and 2. We already computed this. We saw what there were 2 of these. And what I'm going to do, I'm going to remove the largest indexed entry. And then let's see what we get. I remove the 3 from both of them. So this guy disappears and these 2 boxes disappear. And I'm removing the largest index. So what I'm really removing within the content is the last entry. That is telling me to put in the 3s. I'm like, no, I won't listen to you. And I get these 2. So these are of shape 3, right? So these are 2 partitions of size 3. So let's take a look at the Kostka matrix corresponding to n equal to 3. So this is the Kostka matrix corresponding to n equal to 5. Because it's a partition of 5, that's partition of 3. In the shape 3 row and content 2, 1, I see a 1, which corresponds to this guy. And in the shape 2, 1 and content 2, 1, I see a 1, which corresponds to this guy. What's 1 plus 1? You get 2. Let's do that again. Doing another example hasn't hurt anyone. So we look at these 3 guys. Remove the largest indexed entry, so the 4s disappear. This disappears, that disappears. You can see that both of these disappear from the same place. So I get shape 3, 1 here and content 2, 1, 1. So I remove the last entry of each content and my shape changes like that. So I look at the n equal to 4 Kostka matrix again. I look at the row, which is 3, 1, and content 2, 1, 1. I get 2 of these. That's what the 2 means. And then I get shape 2, 2, content 2, 1, 1. And that has a 1. 2 plus 1 is 3. So what are we really doing is we are taking a composition and doing something like a projection. I'm removing the last entry of my composition. I get something which we call beta star. And what I'm then, for beta star, then you remove the last entry. And what this is doing, in order to understand and compute the lambda row beta column entry, I look at the beta star column entry of some smaller matrix. And in this case, we were just adding up those values and they worked out. And what are the columns that we're looking at? There were some special, what are the rows that we're looking at? There were some special rows, right? They're exactly the rows that when you remove the boxes, you get those shapes. So this is a nice recursion that we have. So this is something that we did. This is the general frame that I'm going to describe that the talk rests upon. If you have any A lambda beta, which is a combinatorial matrix, in combinatorial matrix again, and it's sort of recursive in some sense, such that if I want to find row lambda column beta entry, what I can do is I can look at the smaller matrix with a beta star column, look at some rows gamma 1, gamma 2, gamma 3. Those could be determined by what you're studying. Like in the Kostka matrix, they were removing these boxes. They could be something else. And you get these gamma 1, gamma 2. And this is sort of recording which rows to pick. So S lambda comma L beta, that is why telling me you should pick these rows. And it doesn't have to be just a sum. It could be a linear combination. So I could have these entries here, 1, 2, 3 over there. And I could do a linear combination of those entries to find A lambda comma beta. So the general framework is this. I want to calculate something in the bigger matrix. Can I calculate as a linear combination of entries in a column of a smaller matrix? And if you are in the field of study that I am, which is symmetric functions, almost every matrix that you see satisfies this. In terms of matrices, C is kind of abstract. So we should also look at what it means combinatorially, which will be more important for us. So what does this mean combinatorially? Well, you take the largest index things and you just remove those boxes. This gives us a recipe to construct these objects one step at a time. So just a small question. This follows from the definition, but pub quiz. If I look at all of these shaded numbers, right? I'm shading 1 here, 2 here, 3 here, 4, 5, and 6. What do you notice about the highlighted cells? People who know this don't answer. People who don't know this. For people who know this, you can watch the Red Panda GIF. So what do you notice? They're moving down and to the right. That's great. Yeah, that's definitely part of it.
There's no two things on top.
There's no two things on top of each other. Or as we like to say, they don't share columns. Perfect. And we will call these collections. So there were two conditions on semi-standard Young tableau, right? They were weakly increasing left to right. They were strictly increasing like this. And those two conditions are exactly captured in those answers. So the strictly increasing condition is this. They don't share any columns, and we call this a horizontal strip. So let's make our tableau using horizontal strip. In fact, every time you ever see a tableau in your life, think of it as a way to construct your shape. So the ones mean add this in step 1, twos mean add these in step 2, these in step 3, step 4, step 5, step 6. And so it is a way to construct your shape. And this is what the recursion is capturing. Right? I was adding stuff on top of my smaller diagrams. So we now understand how that works on that level. Let's find. So I'm going to present to you an inverse. This is known, by the way. So this matrix right here, our Kostka matrix, has this right inverse. So this times this is the identity. And the inverse Kostka matrix, it is of course not an inverse because it's a rectangular matrix. But I will call this the inverse Kostka matrix throughout this talk. Whenever I say Kostka matrix, I mean the rectangular version. So you can see that the inverse Kostka matrix has only ones and minus ones. Why? We'll see. But this is good because if you saw the Kostka matrix, you could clearly riot and say, why is there so much redundancy in this? Right? This is 2, 1, 1, 1, 2, 1, 1, 1, 2. These columns are the same. Why don't I just get rid of them? But the fact that we have this rectangular redundancy built into our Kostka matrix makes this matrix really nice. And if you take anything from this talk, the fact that we use compositions in this paper is extremely important because a lot of previous work has been done on having partitions. So what are these ones and minus ones? I will describe this object called a ribbon. What does a ribbon do? It goes along the border of the diagram and it snakes like this. And the border is this whole. Whoa, that's really light. So the border is this whole thing. And what I have drawn for you is a ribbon, so it's a subset of the border. And the thing is, it's also called a rim hook and border strip. So if I say some word like that, you know what I mean. A ribbon is called special if it starts in the first column. So its bottom left cell is in the first column. And if I have all of these guys, these are the all possible special ribbons. So they start from the bottom and then they go up. So they always need to start in the leftmost column. So a ribbon goes like this. A special ribbon has to start in the leftmost.
Does it have to start in the leftmost column and the bottom row, or just the leftmost
column? Yeah, so it is leftmost column and the bottom row. So it is like the first sort of cell in this origin in some sense. Yeah. Yes, I can be a little more specific about that, but this will be a working definition. Yeah.
And it has to go like all the way to the end of a row. Like one that went up. So see the one that just is green in the bottom left. It went up by one and then over by just one. That would.
Yes, there is a reason why we do that. So what we're going to start doing is start removing these ribbons. And so if I remove only this, that shape isn't a partition anymore. So that's why these are the special ribbons that we'll be talking about. But yeah, that's a very good question. So to each special ribbon, I can associate a sign. And a sign is basically you look at the number of rows, subtract one, and raise it to the power minus one. So in this case, I have this ribbon occupying 1, 2, 3, 4 rows. 4 minus 1 is 3. Minus 1 cubed is -1. Same way you can find it for all of these, and you get these particular signs. Well, plus ones and minus ones. You know where this is going. So we can construct something called a special ribbon tableau. It has a very similar idea to what we did with the horizontal strips. We were adding them one by one to create our semi-standard Young tableau. Now we're going to do the same thing with special ribbons. The ones tell me to do what to do in the first step. I add that ribbon. That gives me -1 squared. The second one will be this ribbon. That will be -1 cubed. This particular one will be -1 to the 4 and then -1 squared. And then I multiply all of the signs together. And that gives me the sign of the special ribbon tableau I just made. And so this will be -1 or +1, depending on what these particular parities are. And just for context, same thing we did, shape, what are you filling? And that is this shape given here. Content is the same. How many ones are there? How many twos are there? How many threes? How many fours? So shape and content right here. And now you know what we can do. We can just fill it up. Fill our matrix up. The special ribbon tableau, this can be proved, but just trust me at this point. You can either add a special ribbon at every point or you cannot. And so because of that, you can either make a special ribbon tableau, which is unique, or you cannot. And so there is exactly one special ribbon tableau. There is at most one special ribbon tableau of a given shape and content. If there is any, there is exactly one. And so in this case, when I look at the entry -1, it's not coming from multiple objects being counted and canceling out. It is coming from exactly one unique object. So, for example, this guy here, it has shape. Yeah, so in this case, it has shape 2, 2 and content 1, 3. So you read it the other way. And so let's get to the actual main part of this talk that I promised you in the title. Well, this identity holds using matrix multiplication. All of us can do that. But we have been talking for pictures the whole time. Can we show this using pictures? So before I actually get to the climax of this talk, questions? Any clarifying questions? Could you explain this again or also again?
How do you get the special ribbon tableau?
The construction of that or the matrix?
Construction.
Right. So do you understand what special ribbon is?
Yeah.
So they go like this, and they start in the first column. So you can see that the first one starts in the first column, goes like this. Now I pick some part in the second column and start there. And then I do 3, and it goes like this.
But didn't you have to have a tableau in order to get the special ribbon?
You could go either way, because I could start with a ribbon and then add another special ribbon on the bottom. And then I can read it the other way. Ones, fill this with ones, fill this with twos, fill this with threes, fill this with fours. So they're both in bijection. Okay. And then the sign is computed like that.
So a special ribbon tableau is specified by the set of ribbons and the entries to fill the tableau. Is that right?
So ribbons are
just the ribbons.
one of them, yeah.
I saw a raised hand in the Zoom.
Yeah.
So they want to talk.
They're welcome to either talk or
Yeah.
put the question in the chat.
Hi. Thanks. It was really nice listening to your talk. Just a question. Since you're doing this right inverse, I forget, was it right inverse? You're finding right inverse. So the
Yes, it
same
is right
way,
inverse.
can we do the left inverse and then reverse the whole work? Row became the column in your diagram, your ribbons, everything. Do you think it's that straightforward?
Yeah, so that is a good question. So depending on which inverse you're looking at, your interpretations will have to change. So the interpretations that we have work for right inverse. So what we will see something where the shapes will be the same, but the content will vary. But if you consider the left inverse, the content changes. The content is the same and the shapes vary, which is a relatively harder problem. But in this case, like, I don't know. So multiplication of these two does not give you identity for sure,
Right.
or even like a identity inside a bigger matrix. So you'll have to change your interpretations of what you're looking at to get a different setup.
Okay, thanks. I was just thinking about that. Thank you. I appreciate that.
Thank you for the. Or we pass the checkpoint. This is a reminder for everybody to hydrate. Okay. So this is roughly the last slide, which is what other people have done. And after this, we will start talking about our paper. So when people consider the Kostka matrix case, they're mostly looking at the square case. So square case is indexed by partition and partitions. So in the sense, you remove all the redundant columns. And this is what you get. And Kostka matrix is a very true matrix. It maps between bases and bases of symmetric functions. And what people are looking at is k inverse equal to I. That is one of the problems. Agassi, and my grand advisor, they gave a proof. They gave a nice bijection that shows that k inverse equal to I, but their proof used partitions, and partitions require a lot of reordering within them. As we will see, our proof is quite clean. There are other problems where you can swap, you can consider a different inverse, right? So k inverse equal to I is different from k inverse k equal to I. I can explain after the talk if anybody is interested. And this has been also tackled in multiple ways. That is not what we're doing. In this talk, we prove k inverse equal to I and not k inverse k. And there is very recent work by Allen, Solano, and Mason, which sort of builds on the Agassi-Rebel bijections, but they use compositions. But their bijections still have arbitrary choices. Our main selling point for this paper is that the bijection we will describe is canonical. It does not have any arbitrary choices. We are forced by the constructions to choose. Okay, let's jump into it. What are we doing? This is all the objects that we have. Kostka matrix counted by a semi-standard Young tableau, and an inverse Kostka matrix counted by the special ribbon tableau that we saw. Then the fact that this identity holds, that k inverse is identity, is equivalent to checking this particular condition. What is this condition? I'll describe it abstractly, then we'll look at a lot of examples. I start with a partition mu. I remove a horizontal strip of size L. I get gamma. And then I add a special ribbon to get a shape lambda. And this process will have an associated sign to it. We'll see how. If my starting and ending shape are different, I should get a total sign of 0. If my starting and ending shape are the same, I should get a total sign of 1. This is reminiscent of the fact that the off-diagonal entries of an identity matrix are 0, while the diagonal entries are 1. So this is the most abstract way to do this. Let's look at an example. My starting and ending shapes are the same. And what I need to do is remove a horizontal strip and add a special ribbon. How can I do that? remember, horizontal strips did not want to be in the same columns, while special ribbons really want to just climb up columns. What is the resolution? So if I, okay, by the way, also, if I start and end at the same shape, I should remove a horizontal strip and add a special ribbon. So I should remove and add the same thing. So what can we do? Perfect. It is exactly one row. The only thing that is a horizontal strip and a special ribbon is a single row, the last row, because you also will remove the biggest index thing. So I remove this guy. Also, I can't remove anything in the middle, right? That's not a partition anymore. This is 0. So I remove the last row and I add the last row. The sign of this is it occupies one row. 1 minus 1 is 0. Minus 1 to the power 0 is 1. So the sign of this is negative 1 to the 1 minus 1, which is exactly 1. And that's what the theorem wanted. Let's look at the case when lambda is not equal to mu. I start with a shape, end with a different shape by removing a horizontal strip of size L, and then adding a special ribbon of size L. Start here, remove this purple horizontal strip, end up there, and add a special ribbon. This is one way of going from this shape to that shape. How many other ways do you think are there?
Other way?
That's a good guess.
Just shifted like this.
Yeah, right? Like, that's definitely, like, I could remove a different horizontal strip and add a different special ribbon, but I want to end up at the same shapes. There's so many ways I could be doing that, right? Maybe I start removing this horizontal strip, then I get a different intermediate shape, and then add a special ribbon that finally gets me there. So how many different routes are there? I mean, it's a question that, like, nobody, that's the point of the but
5.
no, it's exactly one more. So this will lead us to, there's exactly one more way. That's insane. This is one of my favorite party facts. So the way I'm going to do this, because it's exactly one more, that means there are 2 ways to go from one to the other, and I'll describe what is called a sign reversing involution, which I personally feel is like the grasping at the heart of combinatorial bijections. So this is what the involution will do. Look at your special ribbon. This is called the head of the special ribbon. And you see, does it intersect with my purple horizontal strip? If it does, I push it down. If it doesn't, I push it up. What does that mean? Right? Let's see an example. But this is the idea. I'm going to see, does it intersect with my horizontal strip? There are 1, 2, 3, 4. That's in the 5th position, right? That's where the head is. There are not even 5 here. So that does not intersect with my horizontal strip. So this head, does it intersect with my horizontal strip? It does not. So we are in the second case. And now I push it up, and that means I send it upwards to the next special ribbon that I showed before, and then I sort of pull it back. So what is the intermediate shape? This. And how do I get this shape back? By adding some horizontal strip, and so I get this. I start with the shape, so I describe this process, and then I look at what to do over there, and then I come back. If I count the signs of these, that has sign -1, that has sign +1. You wouldn't believe what -1 + 1 is. And that's exactly what the theorem wanted. So, questions about this? Is this particular step?
And you're finding this doesn't just work for this example, but this is true for.
Let's do another example. So I look at this particular guy. I start with this shape, which is a different shape than before, I believe. I remove a horizontal strip, get some intermediary shape, add a special ribbon to it. By the way, the whole thing that we're doing is actually in the background proving that K times K inverse is identity. And in this case, if you look at where the head is in the second row, that actually does intersect with this. Because, so this guy here intersects with this guy here. And because it does, I push it down. And what is the next special ribbon? It's that one. And then I just pull it back. I remove the special ribbon. I add the horizontal strip that gives me this shape. And if I again were to compare the signs, then -1 plus 1, which is exactly 0. Why this works? That's why it's in the paper. I'm not going to prove that. But this is how you can convert the matrices into pictures. I'll just describe a general idea of what's happening. If you want to prove any A times B equal to identity, where A and B are these combinatorial recursive matrices, right? Two conditions that we have talked about. Once you have that condition, in that case, you can convert this problem into a problem of starting with doesn't even need to be a partition. We could have any objects, but mostly we type with partitions because that's kind of our day job. You start with, say, a partition, you remove some stuff off of it, get some intermediary shapes. In the previous case, we were getting 2 intermediate shapes, but there could be multiple. And you basically sum up over all ways to do this. This will have a sign associated to it. In our case, Kostka matrix, this has sign 1. So I didn't talk about that. So this has some sign, this has some sign. Find the sign, multiply the sign, and all of that should give you 0 for different shapes, 1 for the same shape. And this will exactly prove AB equal to Y. The proof, by the way, is completely linear algebra. There is no combinatorics. But the fact that the objects are combinatorial is very important. So we have done like the main work, right? But it's kind of silly to be like, oh, this proves K inverse equal to I. Yes, it does, but it's an equivalent condition. The objects in the background aren't converting to each other. There is something actually happening. So what does it mean for you to have a bijection that proves AB equal to Y? Like, what is this global bijection? So let me describe this in general. I have a matrix A, I have a matrix B. How do you multiply rows and columns? So we're back to kindergarten. I have lambda here, I have mu here, right? And the multiplication is basically, so the columns are indexed by combination. That is some slight limitation that we have on our work, that all of the columns must always be compositions. So you just multiply these two and add them together, you get that. So every lambda comma mu entry of A times B is this, right? Just matrix multiplication. If this needs to be, yeah, so that is every lambda comma mu entry, but A lambda beta itself was counted by some combinatorial objects. Say some objects T, whereas B, the matrix is also, its entries are counted by some combinatorial objects, say U. And all of these objects have some signs associated to them, right? Sometimes -1, -2, and they're all added together. So instead of just looking at this entry like this, I can just imagine each entry of A times B as a product of signed objects. So you can think of this as, this is a semi-standard Young tableau and a special ribbon tableau pair. So what does it mean for you to actually have a bijection that proves something is identity? It's this, that I'm taking these objects and sort of converting them to other objects that are canceling out. So these signed objects by themselves are canceling out. Then this is really what we need. The other thing is an equivalent condition. That is great. It works, but that's not what the objects are doing. So the way you would do this, one way to do that is by using something called a sign reversing involution. So we take a pair T comma U, and it can be a fixed one, which will be a diagonal entries, or it can change into an object that has an opposite sign of my starting object. So if I sum over these two signs, they will cancel out and give you 0. So this is what I really want to show. And this is our main punchline. using our local bijection, let's create a bigger bijection, the objects. So this will actually show us that K times K inverse is equal to the identity. So on the diagonal, if I look at these two, and I consider the sign of these two objects, this has sign 1 because semi-standard Young tableau always have sign 1. And remember that these rows had a sign 1. So if the special element tableau has sign 1. And this is my fixed point. So sine of this times the sine of that is equal to 1. And these objects are my fixed points. These are what my diagonal entries are. So this will give me that the diagonal entries are indeed 1. But let's look at the main bijection, what this is doing. I start with these two objects. You can compute its sign. It is -1. So the sign of this pair is -1. Can I create a pair that is unique? So it is an involution. So if I create a pair, I also get this pair. So it's a pair of pairs such that that has the opposite sign. Well, let's do that. So I start by removing the largest entries, the same way we did in the beginning of the talk. I get this intermediate step, and then I again remove the largest possible entries, and then I get the same shape. So this is a process that I do. I get over there. And now what do I do? Well, there is exactly one way. Remember this? So the thing on the top is exactly this process. So now instead of this process, I want a process here that corresponds to this. And so I will choose that process. And that's exactly. And now I restore my force. And the way we have constructed it, every other step has the same sign except this, where the sign actually reverses by our initial way. And so these two steps, they cancel out. And this is actually what the objects are doing. So this is a bijection on the level of pairs such that they are always canceling out. So great. We never actually multiplied matrices out, and we have proved that they are inverses of each other. In the last couple of minutes, I'll just do a rapid fire of other application in case that interests you. Instead of special ribbons, you can define these called ribbon tableau, which is tableau made out of ribbons. And I want you to just focus in every example what we are doing. Remove this, add that, has a corresponding remove this, add that. And what this shows is actually that the characters of the symmetric group are orthogonal. So this is a visual diagrammatic proof of that. Then there are these matrices. I'm not indexed them, but they are sets. So if a set is a subset of the other, I put a 1. If it's not, then I put a 0. Does anybody know what the inverse is? What does it mean? That's fine. I will say that. So the fact that this is equal to the identity, you can prove it using this thing called composition diagrams. Again, remove, add, opposite sign, -1 + 1, 0. Right? It's the same flavor. This is, by the way, inclusion-exclusion principle. So this is a diagrammatic proof of inclusion-exclusion on the lattice of sets. And I just want to make sure that you don't go away with this talk with this misconception, because we had that for a while. The intermediary objects, there could be multiple of them. In our case, we always had 2 intermediary objects, so they had an involution between them. But that's not always the case. This is a case where these objects, there are 3 of them. And I don't know any refinement of this that will make it into an involution. So there are 3 objects, and they kind of just all cancel out together. So there's that. Please. Oh, wait, actually, it did get published. I didn't actually realize when it got published by advice, but like, did you know that? I don't know how I just missed it. So there are some other things that you can do. If you care about quasi-symmetric functions or non-commutative symmetric functions, these are really good for that because compositions are really involved in those kind of functions. Our proofs are, in a sense, canonical because at each step, right, when we reach that point, we had no other choice but to do that step. So we do improve upon a lot of known bijections. I do believe this can be applied to a lot of other fields. I don't know a lot about other fields. So if you see this, one example that I did was Hadamard matrices, which are like these recursive generated matrices. And our process gives you that Hadamard matrices are sort of self-inverses. There's some constant, but so you can show that. Finally, if you, there's the proper paper, but this is the archive link. And just a final thing, a friend and I, so I used to organize the GOCC Graduate Online Computers Colloquium. And one thing that I have started with the current organizers is to just put feedback forms at the end of the talk, because Jody Williamson said that we don't give honest feedback to each other. So you can scan this QR code and give me feedback. I did it in my previous talk and I got really good feedback. So please fill it out at your own time, and that would be really nice. Thank you.
Hey, thanks. Any questions in person?
I was curious on the set one, but you were indexing it by any sets on the rows, any sets on the column, or same sets, and I was curious about that.
Yeah, so it is, these are sets, and I think they are ordered by any linear extension of the inclusion, that is. So I take the sets here, and I take the poset of inclusion of lattice. So
Either by one at a time or any number of times.
what do you mean by one at a time?
Like, you mean like you have a set, you could add a few more things in, a few more things in.
Yeah, oh, right. So these are sets of a, yeah, so it will be like one. Yeah, so you start with the set, and the set that comes below it must contain it in some time. So
That's what.
So, okay, let me phrase this properly. So you start with the set inclusion lattice. So you start with the empty set, and then you add an element, then you add all the elements of, so size 2, size 3 until size n, and then you find a linear extension of that, and then you put the sets. Right? Does that?
The same on the columns you have.
It's the same.
Similar. Okay.
Yeah. So it is a square. You can also think of this as being indexed by compositions. It's bijection.
Other questions? About on Zoom, anything? All right. Now let's thank the speaker again. Thanks.
Someone in the chat? No.
It says thank you.
Thank you.